Let me briefly introduce our special guest. Dr. Rabier has been Director General of the European Centre for Medium-Range Weather Forecasts since January 2016. Under her leadership, the Centre made enormous progress in quality and quantity of products, also extended the premises from the UK to Bonn in Germany and also in Italy. Before she was 2 years Director of Forecasts at European Centre for Medium-Range Weather Forecasts. Her outstanding career started at Météo France, if I'm not wrong, and then proceeded at the European Centre. Dr. Rabier is internationally recognized expert in numerical weather prediction, and she is well known for her key role in developing innovative data assimilation method, which contributed to an optimal use of satellite data. She also led an international experiment involving a major field campaign over Antarctica during the International Polar Year and WMO THORPEX program. She is chairing the Advisory Committee for Earth Observations of the European Space Agency, ESA, and she is a member of the International Scientific Board of the International Foundation Big Data and Artificial Intelligence for Human Development. She has been awarded one of the highest decorations awarded by the French honors system and the Great Prize of the Air and Space Academy. She is also honorary member of the American Meteorological Society. Last week, she was one of the keynote speakers at the European Meteorological Conference in Bonn. Please, I would like the audience to hold your questions until the end of the presentation. So the floor is yours, Dr. Rabier.
Thank you very much. Thank you so much for the introduction, and I'm really happy to be here and give this talk to you. It will be quite a general talk, but if you have some more questions, please, I'm happy to take some questions. But I wanted to introduce everything we do at the center. Should I stay close to the microphone for maybe remote? Yeah, okay, I will stay around here. So this is ECMWF, this is our emblem, and we have to change it regularly according to the number of member states and cooperating states, because we have the privilege of welcoming new ones. So lately we had Estonia joining as the last member state, and we also had Georgia joining as cooperating states very lately. So we now have 35 states in Europe and beyond supporting us. But we were created a long time ago when it was all in black and white, and it was mainly men in grey suits. Okay, you don't have color, but I'm sure they were in grey suits. And the only ladies were the secretaries giving away the papers around them. And they were smoking in the room as well. So it was very vintage photograph. I actually love this picture. This was in 1975 when we were created from a convention. It was then not so many. We were less than 20 member states. But actually, at the time, Yugoslavia, the former Republic of Yugoslavia, was among the first ones to join this joint enterprise. So this is now our footprint. You have in dark blue the member states, 23 of them, and in light blue the cooperating states. As you can see, it's very much European focus, but it's not EU. And it goes beyond, and we go as far as Morocco and Israel in the north. And of course, we have Iceland as well. And as I say, the easternmost, we have Turkey. We had them from the beginning, but now Georgia as well. And our premises had been in Reading since 1979. We had a new building. It was actually opened, the ceremony, by Prince Charles at the time. So the current king of the UK opened our premises in Reading. But we opened a new data center last year in Bologna, because our premises at the time, it was full of fields around, and we could make as much noise as we wanted with the dry cooling of our computer, etc. We could expand, but now we have accommodation around us, so it was felt that we really couldn't have the next generation of computer in our premises, so we looked for a new place, and Bologna offered us a renovation of a new center. And then our partnership with the EU meant that we couldn't continue to run big EU programs from the United Kingdom since it's left the EU. So we looked for another place, and this is where we opened the new premises as well last year in Bonn. So just a couple of pictures. This is our new data center in Bologna. It was refurbished data, which was a tobacco factory, actually, in Bologna, but it doesn't smell of tobacco anymore. Now it's brand new, and we have all our computers there. And our archive is actually, at the moment, transiting between Reading and Bologna. So we are really a bit scared about what could happen, because our main, pride and resource for users is our archive. Bologna, we will have a flashy building from 2026, 2027, but at the moment we are hosted in the Ministry of Environment of BMUV in Bonn. But of course, we, as all scientific organization, we have partnerships all over the place. We are not just having partnership in Europe. Our closest partnership is with our member incorporating states, but we have cooperation agreement with NOAA in the US, with ACMAD in Africa, with the CMA in China, INPI in Brazil, etc. And of course, the scientific communities goes well beyond. We have some ECMWF fellow. We contribute to some of the programs, in particular for training, etc. So I think our reach is probably global, even if we are European. So as I said, collaboration with the EU. So all our member states are not from the EU, but most of them are. But we started a very productive collaboration with the EU we started a long time before that with European projects. But in particular, since we started running the Copernicus, 2 of the Copernicus services on behalf of the EU, we were entrusted entity, as we call them. And now this new initiative, Destinationer. So I think it's really beneficial that all our member states benefit from this close collaboration with the EU as well. But we are definitely not an EU agency. So our deliverable, our title is Medium Range Weather Forecast. That's what we're here for. And our main deliverables is numerical weather prediction. So we don't have forecasters. We have what we call analysts who check the forecast every day. But they are not real forecasters. We are not issue bulleting. We are not gathering observations. So we are definitely not as broad as a Met service. Really, our remit is only numerical weather prediction. But we try always to push the limit of this and the quality and how far we're going. So we do the medium range up to 2 weeks every day. We do what we call the extended range. We used to call it monthly, up to 6 weeks, twice a week. It will change soon. And we do the seasonal range up to 7 months every month. And then we have a lot of deliverables in terms of environmental monitoring, what we call environment, through the Copernicus. So we run the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service. So in terms of Copernicus Climate Change Service, which we call C3S, we do this monthly bulletin climate monitoring, particularly over Europe. And then we predict as well the atmospheric composition on the other service. And a very big new component in this new phase of Copernicus is preparing for CO2 emissions monitoring. So that will be, of course, a key part of, checking that all countries sort of respect the Paris Agreement and we go towards net zero. So we will put a sort of verification support system so that people can check whether their inventories correspond more or less to what can be seen from the sky, from the satellites and numerical modeling. We also run the computational part of the emergency management services for flood and for fire. So we produce these EFAS and GLOFAS and also some fire risk danger. So we've had the new strategy from 2021, and this is in terms of science and technology. These are our goals for the next 10 years. So in the first one, I think all the words are important. So it's a seamless ensemble Earth system. So Earth system, because we don't just do the atmosphere, we do all the coupling with all the different components, and in particular with the ocean. Ensemble, because we believe we don't do a good job if we just have one single, what we call deterministic forecast. We need a few, and in particular, we are running an ensemble system. and seamless because we go from the analysis, short range, medium range, extended, seasonal, and we try to harmonize this as much as possible. So now our great focus, and I'm afraid I'm always focusing a bit more because of my own expertise, but a lot of our focus is on using observations, and in particular satellite observations. So we want that our Earth system maximizes the use of current and upcoming observations. We all spend, our member states spend a lot of money with these new flashy satellites, and really we have to make the most of them. And I think it's not spending too much money, that at least doing the research to actually extract as much information as possible through all the observations. We want to do that through consistent and accurate modeling with realistic water, energy, and carbon cycle. So we want our system to be close in terms of these cycles. And we were very, water and energy was at the forefront of our preoccupation, but carbon cycle is becoming more important now, especially as we are running this CO2 monitoring and verification system on behalf of the European Union. So how do we do that? We want to use advanced high-performance computing, big data and AI methodology to create this new buzzword, digital twin of the Earth, with a breakthrough in realism. So our resolution is not that high for a global model, but we really want to push the limit of the resolution and go as close as possible to what is useful for the forecasters. So of course you know all that, but we capture the weather globally with all these different instruments. We have these, our systems have been fully coupled for a while now. So we have all our forecasts are fully coupled between the atmosphere, the ocean, and the land, and the sea ice now as well. So which means that they all interact with each other. It had been coupled with the waves for quite a long time, but now we also have this 3D ocean model fully coupled with our atmosphere model. And for this, we gather all the information we can, and in particular, we ingest 800 million daily observation. We use about 1/10 of that in our system every day. As I said, ensemble predictions, so we have already an ensemble of data simulation. So from the beginning, we don't just say this is the atmospheric conditions. We have one reference one, but we also have all this ensemble around it to really reflect the fact that observations have some errors, our way of assimilating them have errors, so we can't really show just one picture of the atmosphere, even at the beginning. And then, of course, we have the model running, which is not perfect, and for which we have some perturbations which reflects the uncertainty in the parameters. And then in the end, we have a distribution of ensemble members. We have 51 of them. And that represents the different scenarios with their likelihood of happening. A big part of our job is also to always check the performance of our ensemble. And we do that with WMO in particular. We exchange scores, but this is typically what we show to our member states. These are our headline scores for the medium range and the extended range. So for the medium range, for the ensemble, what we show is the CRPSS for 850 hectopascal temperature. You have the smooth line, that is a smooth one, but then you have the annual cycle as well in blue. As you can see, it's going upwards, and quite satisfactorily actually for the ensemble is going upwards at more than 1 day per decade. You know, for the deterministic forecast, we say that usually the rhythm of progress is we push the predictability by 1 day every 10 years. I think for the ensemble, we have been doing a bit more than that, which is quite satisfactory, but there are some variations, and sometimes, like in 2010, there was extra predictability in the atmosphere. We thought we had hit the jackpot. Oh, wow, the model is fantastic. But no, it was not the changes we made. It was actually every model had a big increase in skill, and then it went down. So this way we could justify that going down for a couple of years was not that we had introduced a bug in the system, but it was really that the predictability was high before that. So we should look at the general trend. For the monthly forecast, well, the quality is much poorer than the medium range, but also it's very variable. And so what we do is we actually run some reforecast, and that's what we compare in terms of checking our quality. So it is going up, and in particular, it has gone up since ERA 5, because the reforecasts are based on, initialized on ERA 5. Here we have 2 verifications against the analysis and against synoptic stations. This is getting a bit more deep into the performance. This is at day 5 for the Northern Hemisphere, and for different parameters. So it's nice to see that they all increase more or less in line, and in particular also we check that the weather parameters, because that's more important for the forecasters, of course. One way to validate the model is also to look at simulated data compared to real satellite data. So this is one comparison with GOES, the GOES satellite. We do it as well with Meteosat. And it's quite interesting to see that even at the global scale, our model on the right-hand side is really quite simulating the main systems quite well. Even if we are only at a 9-kilometer resolution, we can see some of the big patterns. We can also see the discrepancies, and that's what's interesting, Do we have too many clouds here or there? Is the ITCZ well represented, etc.? So I think it's quite interesting to do that as well for diagnostics of our model, not just scores, but really looking at the fields. We also, of course, use the in situ observation, and we verify, in particular when there are special events, we verify with all the data that we receive, and we don't always receive all of the local data that you have. Recently, I showed that at our council at the end of June. This was the first big heat wave we had this summer. Since then, we had quite a few. But this one was a very early one in June over Western Europe. And we have what we call as a product the EFI, for Extreme Forecast Index, that really shows how exceptional the weather is compared to climatology. And we have the verification on the left, which is the EFI for temperature, which really shows, yes, this is going to be quite intense. The 6-day forecast on the right, we could see something was happening. You could say it didn't extend maybe enough to the west, in particular over Spain there. Maybe we kept it a bit too much over the sea. Something that did hit the headline in France, and I didn't choose that by randomness. Actually, I was born in Biarritz, so this is my hometown, and I very much know this phenomena, which is what we call galerne in where I am. So when suddenly it's very, very hot, but suddenly at the end of the afternoon you have the clouds coming in, the wind changing, and suddenly the temperature dropping. So I've been witnessing these events a few times in my life, and in particular, this was the highest temperature ever recorded in Biarritz, happened in this month of June, which is very early. 42.9 degrees, this is something on the Atlantic coast. Usually if we have 40 degrees, it's extremely exceptional. This hit the maximum by more than 2 degrees, so it was really much higher. But what was more exceptional is that there was a 20 degrees drop in temperature in just 2 hours when we had this galerne coming and the westerly winds coming then along the coast of the Spain. And so you have all the observations are in white, the ensembles in blue, and the high resolution in red. So obviously we don't have the right amplitude because we didn't manage to get as high as 42.9 degrees. But I think it's quite exceptional that for a global model we could reproduce this increase in temperature and then this sharp decrease. So as I say, the amplitude is not right, but I think it was really quite good that we could simulate this. And of course then we had a lot of heat waves coming back over Europe, as we know, this year. Now, what about what we did in our plans and how we improved the system? We had 2 main developments last year. We had 2 new cycles. Well, we call cycles the new cycle of the model when we introduce a lot of changes. So unfortunately, we were a bit late in switching to a new computer, but we used the time to actually put some scientific changes in the model that didn't require more computing power. What we did in spring 2021 is to introduce this single precision in the calculations of the model. So usually we run in double precision, but then running in single precision and checking that everything goes fine, we can save 40% of the computer time, which is really not negligible at all. And this allowed us actually to increase the vertical resolution of our model in the ensemble and extended range from 91 to 137 levels. So we immediately recycle. We don't like to keep our computer inactive. So as soon as we make some progress in efficiency, we use the extra time we have on the computer to increase the model, the realism of the model. In the autumn 2021, and I'm sure your forecasters might have seen the difference, we introduced this moist physics upgrade. So this was a whole revamp of our moist physics. So we changed quite a lot, the clouds in particular. And we changed some other things in observation, data simulation. What we are planning for the spring, so first on the 18th of October, very soon now, in a month's time, we will switch to a new computer, so that delays the next implementation. This is just a switch model for model the same, but it means that we cannot do an implementation of science at the same time. But the one we are working on now, it's going to be a big change. The ensemble resolution, we go from 18 kilometers to 9 kilometers, the same as the current deterministic model, high resolution model. The extended range will be very much changed from running twice a week to running every day. And it will have 100 members. So it has 51 members, now it will have 100 members. So a big change in the extended range. Then we'll also introduce a multi-layer snow scheme. In terms of infrastructure, we have this OOPS, object-oriented prediction system, which will go in. And so that's among other things. And we also have hybrid linear ozone that we will introduce. Big change. The next one will be an improved surface with a new version of the model for the ocean, for the sea ice, updated land field as well, land use, land surface type. And this prepares for the new seasonal scheme, which will also have 100 ensemble members. And we will prepare the new reanalysis, which will also be coupled with the ocean. So I'm going to talk, so really one of our aims in our strategy is not only this coupled system in the forecast, but really coupled data simulation, so that what we do in analyzing the observations used through the different compartment of the atmosphere. So we are working on a scheme to do coupling within the data simulation cycle. This is something that had been tried in the reanalysis, but otherwise we do weak coupling, that where one analysis in the atmosphere influences the ocean in the next cycle. We have now a new project which is doing our own analysis of the sea surface temperature rather than relying on something which is done separately by the Met Office, because it changes. Instead of having a sea surface temperature value once a day, then we know that it changes more quickly. So this is something that we are doing at the moment. It's very experimental. It doesn't go into a cycle soon. We know that our satellite data have some information on the sea surface temperature when there's no cloud. So usually what we do is, when we do the analysis, we use the sea surface temperature, well, the skin temperature, as a sync variable. So we adjust it, but then we throw the information. We just adjust it at the same time as the atmosphere, but then we discard this information. So the idea was, why don't we use this information to pass it on to the ocean, actually? And this is what we are doing now. So we are trying that. And what we see is that when we pass this information from the skin temperature to the SST, then to the ocean model, we actually improve the ocean depth, not only the surface, but even a few meters down. This was comparing to Argo floats, and so going down. And then what we see is that actually, because the ocean has got this memory, it can feed back to the atmosphere. And so we could see that what is on the left of the 100 line means that our first guess is better. So then we improve the first guess in the atmosphere for the next cycle as well. So I think this is quite promising, and we are working on that, as I say, not for tomorrow, but I think this is a very promising area of research for us. So we are also working a lot with the space agencies, EUMETSAT, ESA. We are working with WMO on optimizing the global observing system. So we are always documenting what do the observations bring to our forecast. what is the importance of any relative observations, and then we try to plan for the next ones. So this is a bit complicated, but this is done with the iJaunt model, and it's this forecast sensitivity to observation impact. So you have the different observation types with the different colors: microwave, water vapor, microwave temperature, infrared temperature, water vapor, GPS route occultation, aircraft. And you have in time how much they contribute to our, this is computed for the short range forecast, but we could document that it persists in the medium range. What was very interesting in this one was the pandemic in 2020. So it's at the beginning there. So the pandemic meant that the aircraft didn't fly anymore. And so you can see the aircraft there in cyan, in light blue. They were about 15% contribution to the forecast quality. And then they suddenly dropped to 5% because, of course, we didn't receive observations from the aircraft anymore. So that was a big drop. And, you know, people were asking us, journalists or something, did you see a drop in the quality of your forecasts? Well, we might have seen, but on the other hand, at the same time, we had an increase in other sources of observation, which sort of picked up the information from the aircraft. This was the GPS radio occultation, because we had 2 new constellations of data that came in at the same time, and they measured temperature and humidity, so they are quite useful. So this is the orange line, GPS row, where you can see that at the same time, I mean, it was coincidence, but at the same time as we dropped the aircraft, we had the GPS row, a new constellation coming, Cosmic 2, and then we had this private company, Spire, which takes the measurement and offers the data that EUMETSAT is buying now, who said at the time they didn't have an arrangement with EUMETSAT, but they said, if you want, we can give you the data for free for a while, because we know that you are in the pandemic, we know you have less data, so you know, we can give you the data for free. So that was actually quite welcome. We say yes, of course, but because we knew that EUMETSAT was in discussions with them to use them, and so they provided that for a while. They didn't provide it forever, but this was quite beneficial, and we saw that it picked up some information as well. So this is just for the story that it's quite nice to not only say, yes, microwave contributes a lot, then infrared, etc., but it's also to see how it changes in time. And I hate showing that to people who actually maintain some in situ observations, because it looks like they are not very useful, which is what we are saying to people. It's not true, because they are really anchoring the system. It's not that, yes, the satellite data, we have probably 98% of our data coming from satellites. So, of course, they have a large influence. But if we didn't have in situ, and if we didn't have radiosonde in particular, we wouldn't know how to calibrate and use this forecast. So it's not true that this is only one part of the story. We can only use satellite because we have in situ observations. But on a day-to-day, they have less impact than what we think they do in the whole system, if you see what I mean. So it was maybe a bit complicated. But then we also do, they always say, what, you know, for instance, ESA and EUMETSAT says, if we have a new microwave constellation, would it be better to do how many satellites flying in one sort of constellation, measuring temperature, water vapor, or just water vapor? What would bring the most? This is very difficult to answer because we don't have the data. So quantifying the impact of data you don't have, it's more difficult. But we have new ways of doing it, and in particular we have this new system now with the ensemble of data simulation, where we can actually simulate this, and we are working with the space agencies on that. So as I said, we're also documenting through observing system experiment. This is something different, where we run the whole system with all the observations, and then we do some parallel systems when we remove observations, and we check how much did we degrade the forecast when we removed all the microwaves, all the infrared, all the GPS radio occultation, and all the scatterometer data, and all these new Doppler wind LiDAR, these Aeolus. So this is quite interesting as well. You see the big bars are where the observations used have the most impact, and there you can do it through the whole medium range, which is quite interesting. Something quite interesting I find is that actually, because the latest one was this Aeolus from ESA, which is a research satellite. It was very expensive. It took 10 years more longer to put in space, a lot of technological problems, etc. But meteorologists knew that if you can measure quite directly the wind, you will have a huge impact, because the wind, influences the weather quite a lot. And we have so much instruments on temperature, we need the wind. So people were saying that for a long time. And you can see that actually at day one, this little satellite, just one little satellite, has already quite a lot of influence. And actually in proportion, it grows through the medium range. So really this shows the importance of wind measurements. Now we also do this for WMO, measuring the different impact of different observations. In particular, we are contributing to this SOF, which is the Systematic Observation Financing Facility. I hope I had the acronyms right, which is an initiative by WMO to have some donors country, rich country, actually paying for sustaining the global observing system in parts of the developing world. And so what we measured here is the difference between the influence of one observation in data-rich countries, like continental US in red or Europe in pink, compared to less data-rich, data-dense areas, such as Australia or the Pacific Islands. And what you can see is that the relative value of one SYNOP in the Pacific Island is about 4 times, in terms of global forecasting, 4 times more influential than one data in continental US or Europe. This is because, it's obvious that even if observations are not fully redundant, if they are isolated, they will influence much more the weather in their neighborhood. So we produced this plot to convince people that it's actually very important for global weather forecasting to have a global observing system. And we know that SYNOPs and we did the same for radiosondes, are very important to us. Now, so sorry, I told you that data simulation is my trip, so there was a lot on that. But of course, we don't do just data simulation. We do a lot of development in the model, etc. And the new thing in our strategy is really embracing this concept of machine learning, artificial intelligence. And we have a lot of projects at the moment. So at the moment, it hasn't been quite structured. It has been more, where could we apply some of this machine learning in observation quality control, in data simulation, in reproducing, emulating parts of the forecast, in the post-processing. So we put together this group of volunteers from ECMWF who were keen to try things. And we also applied for European projects to have some also new young scientists, in particular data scientists, working with us on trying to see what could we do with machine learning in our whole scheme. We don't think that we can replace the whole system with machine learning. Some companies are doing that. But we believe that there is a place for machine learning throughout our workflow. So how do we progress? So I told you it's all a bit not disorganized, but this sort of bubbling up of different initiatives. We also have something a bit more structured now with this Center of Excellence we've created with Atos, our new provider of HPC. So Atos and partners, actually DDN and NVIDIA, they are putting some resources, some scientists, to work with us for the new generations of models, how they will work on the new generations of supercomputer, and how to, so this is the bottom right there, with NVIDIA in particular, to gain insight into domain-specific challenges in earth sciences for machine learning. So we also have these more structural activities with some big partners. This is just one example of where we try to emulate one component of our model through machine learning. Radiation is a very expensive part of our model. We tried also to emulate the whole radiation by a machine learning code. This is not quite at the level where it's as successful as our full physical model, but I think it is already showing that it has some promises. But also we were thinking, we have another development, which is introducing 3 cloud effects on this code, on these radiation codes, instead of just downward, upwards. So this is the Spartacus code, which is much too expensive. It's good for research, but we can't put it in the operational model. It's too expensive. So the idea was, could we at least simulate this part of the radiation code with machine learning? And actually, it looks quite promising from a first try. So on the left, you have the impact of the 3D clouds on radiation, on the long wave and short wave heating rates, in the troposphere in particular. So you can see the different changes. And on the right, you can see the same but reproduced by machine learning. As you can see, it looks pretty similar. So I think there is some maybe future for this sort of development. This is just one example. Now we are also very busy in adapting our codes to the new generation of computer, this new hybrid architecture, in particular CPU, GPU. We are not ready to jump on a GPU system, but our hope is that for the next procurement, maybe we would have a system where we would have a bigger part of GPU processors. And again, we are working with, in particular, NVIDIA to optimize, this is for the spectral transform library on different machines and also on with different ways of doing it. So this is how it scales with the number of sockets. This is the time it spends for it. We spend for one time step of doing inverse and direct transforms. So you hope that putting more sockets, of course, you will decrease this time, so good scalability. So on our current Atos 1 complex, we have the white line, and then we try different flavors of using GPUs, and you can see that we can get, with some efforts of coding, we can get to a much better performance, so making it quicker. Also, efficiency is not just in running the code and running it fast, it's also, if you run a big model, high resolution, fast, you produce a lot of data. And a lot of data means a lot of archive. And we actually spend the fortune on our archive as well. So can we do better rather than just storing all the fields? So we always try to diminish the amount of fields we are storing, etc. But we have now new promising developments which we want to continue in the next year or two, to maybe implement them in a couple of years, to do some compression in the GRIP2 coding. And so we think that we can have 35% savings in the new system with 9-kilometer ensemble if we do this for GRIP2, which is from the gray to the purple or blue thing. And then when we change from GRIP1 to GRIP2, then we will have even more savings. We could reach 45% savings in terms of size of the archive, which is absolutely non-negligible. So I think it's worth, we are arguing that we should put one person for 2 years to work on that, to implement that. I think the expense of one person's salary for 2 years, it's completely overwhelmed by this, the price of the cost of the archive. Now, Copernicus Climate Change Service, we are then running it. We are of course, contracting a lot of companies and organizations to run it with us. But this is what we are doing at the center, as our contribution to the Copernicus Climate Change Service. We are running this reanalysis that everybody is using in the Met services, but also in academia and also the energy sector to know where to put the wind farms and etc. So we have a lot. Most of our users of the Climate Change Service actually are using this reanalysis. This is really our most popular product. So we have more than 130,000 active users of the Climate Data Store, and more than 100,000 are using the reanalysis. We were quite proud that in the latest report from the IPCC, the reanalysis was quoted more than 200 times. So it's also very much used for policy making. Well, hopefully this will be used for policy making, and there will be some actions from these reports from the IPCC. We're also running a multimodal seasonal forecast. As you know, the quality of the seasonal is not as high as the medium range, of course, but you can do better by combining different systems. And we are combining with a lot of European global models from Italy, Germany, France, and we're also combining now with Canada, with Japan, and with the US, and Australia is coming soon. So from this, we also, every year, we publish a European state of the climate. So in particular, last year was quite extreme, with plenty of heat waves, of floods in Germany, etc., fires. So we do, this is a very short report, so if you have some users at high level that, you know, are not very much specialists, I think we try to make it for people who don't, are not speaking so much of our language, this European state of the climate. But every month we produce a bulletin to show what is the state of the climate as well. Now we are working as well on atmospheric composition and forecasting and analysis and forecasting. In particular, you remember at the beginning of the pandemic, this seems like a long time ago now, but there was all these things, oh, pollution has decreased, this is all due to the activity stopping in the, you know, in the different member states, in particular some very industrial areas, etc. Well, actually, in particular, ESA was showing all these things, and it has stopped a lot in March, etc. I think we, as scientists, we know that it's a bit more complicated than that. So we, of course, we look at what the analysis tells us, but we know that these surface concentrations of pollutants are very much depending on the weather as well. It's not just the emissions, it's also the weather. And in particular, in February there, before the activity was stopped, because before the pandemic, we had actually low concentration of these NO2. This is in Torino in Italy. And this was not explained by the emissions. This is because actually it was a bit warmer, the planetary boundary layer was higher, and so there was more diffusion of these emission pollutants. So then, of course, after that, in March, the lower pollutants were due to the loss of emissions, etc. But so we monitor, but we also try to explain actually what comes from the different things, emissions. But let's not forget the meteorology also plays a part in it. Now, Destination Earth is this new initiative that we have together with the European Commission, and this is an initiative that started being in the thinking for more than a couple of years, I think. And actually it converged between this green ambition of the EU, but also this digital ambition of the EU. So this is, I think, combining it really, the strategy for data, the Europe digital future, but also the European Green Deal. So the idea is really to do a breakthrough in simulating the climate and the weather through high-performance computing, but in order to help for the Green Deal in particular. So we are three entrusted entities, ourselves, ESA, and EUMETSAT. So these are our usual partners, so I mean it's quite nice because we already know how to work with them, and I think we are quite complementary in bringing each something to this joint initiative. What we are particularly doing is the digital twins. So, of course, we are doing that with the community as well, but this is our responsibility in Destination Earth to deal with the digital twins compared to ESA and EUMETSAT. So what are these digital twins? It's better simulations based on higher resolution, more realistic models, better way of combining all observed and simulation information from the entire Earth system, but also through the coupling of the weather, but also other elements, water, energy, health, leading to better actions. And then having this interactive and configurable access to all data models and workflows. This is a big ambition. We know the first phase of Destination Earth is for a couple of years. We are not going to do all that in a couple of years. So it's nice words, nice concepts. We are working towards that, but we really hope that it will develop in the following phases of Destination Earth. We're already planning the second phase, actually. So this is why we are so excited, and we've been producing that for a while, because we sometimes have access to these very large computers at the center. We don't, I mean, we have a large computer, but not one of the largest computers in the world. But we had won an award to run on the largest supercomputer on the world in Oak Ridge Laboratory in the US. And this was called the Summit computer. And so then Niels Veddy and co at ECMWF could work on running a 1 kilometer model global at the time on their supercomputer. So we had some billing units that we could use and run there. Of course, it required quite a lot of developments, but we could do it. And then we worked with NVIDIA to actually work on the visualization of the results. So this is when we simulated, in particular, this Hurricane Dorian in August 2029. So this is the simulation there on the right of our 1 kilometer model. and it's NVIDIA doing this very fancy simulation. So as we discussed previously, this is actually quite nice for people to show the potential of going to higher resolution. Of course, here you are used to running things at higher resolution in, you know, in your limited area models. We are, with a global model, we are way behind, you know, we are 18 kilometers resolution. So for us, seeing that globally, of course, is really quite a breakthrough. So just a nice animation. We are not going to learn much about meteorology by looking at that, but it's a nice way to convey the power of higher resolution. And of course, tropical cyclones are quite a beast on their own, which are always striking the imagination. So as I said, we are 3 partners in this initiative. We are responsible for the digital twins. EUMETSAT is responsible for the data lake, and ESA for the core service platform for which the users will interact with the different digital twins in particular. We are responsible for 2 twins, the weather-induced and geophysical extremes digital twin and the climate adaptation digital twin. So the weather one is to provide information for a few days about weather and selected environment properties, like flooding, for example, to enable better assessment of the impacts of extreme weather. And the climate adaptation is doing runs over several decades and explore the impact on different sectors. Thank you. So we are just running. This, of course, will be done by the community. We've done an ITT for the climate. We are not doing climate modeling, so this will all be done by the community. We have done a big ITT for the weather one, but we are at ECMWF going to run the normal global, what we are usually doing for the extreme twin. So we are also contributing on our own to the extreme twin, a bit like what we are doing for Copernicus, where we are running the reanalysis, but then there are regional reanalyses, etc., run by the member states. So then plenty of other partners. Importantly, the Euro HPC, because we are going to run on these big platforms, Euro HPC financed by the joint undertaking. And also we are going to have other partners. We are going to make sure that it collaborates well with Copernicus and with initiatives, of course, in our member states. Something that we've been working on, this is just one example of how we work sometimes with the community to support it. Ukraine is neither member states or cooperating states, but we could benefit, they could benefit from this CMUS project, which you know very well, of course, to have a web interface and to have access to products. So in particular, they can access some of these charts. And also we have been supporting CIMA as part of a project by DG ECO in the Commission to support the humanitarian emergency, so providing bulletins for Ukraine. So we are also going back to having some physical meetings for our workshop, training courses, seminars. So, of course, we had to switch to completely virtual in our last 2 years. But I think this is really a key part of our engagement with the community, with the member states, with the Met services, that we have all these training courses and events. And I think that's broad brush what we are doing at the moment, what the future will hold for us. And that's all for me. Thank you very much for your interest and your attention.